This video is about the latest iteration of a project I'm now calling the CW machine, as it both sends and receives. It's a project I've done several times before, but for this version I wanted to use Waveshare's 7-inch LCD dev board, which is built around the ESP32S3 and a 7-inch 800 by 480 capacitive touch display. Because this board is so complete, and to keep the build side of the project simple, for much of the external interface I made use of off-the-shelf breakout boards. Like before, on the send side, the project uses a Bluetooth keyboard, which I'll detail later in the video. Now, recognizing the limited interest in the project's purpose, I'm going to mostly focus on things that I found challenging as I migrated to this development board. The thinking being that anyone considering this board will likely find themselves sorting out the same issues. To be clear, this board, in my opinion, is a first-class product, and the LVGL graphics package that Waveshare promotes is likely a good fit for many applications. And we'll say, in the end, I am pleased with the finished product. When I received the unit, the first thing I noticed was how well it was packaged. Compared to other TFT devices, which arrive sometimes cracked because they were shipped in little more than a padded envelope, this was almost like unboxing an Apple iPhone. I was also pleased to find the package includes pre-made pigtails for the board's interface jacks and headers. Along with 4 small standoffs to further facilitate mounting the display. And to polish off the unboxing experience, the board was pre-programmed with an impressive demo. That last feature would prove to be a lifesaver because it confirmed the unit arrived in working order. Long story short, it would be several days with me doing the compiling before I would see it work again. Now, at the risk of over-explaining, I'll back up a bit and review where I was coming from. Hardware-wise, the previous iteration was built using the ESP32 and a 3.5-inch SPI-type TFT display. The programming was done with VS Code, Platform IO, and Express's IDF framework. So, my thinking was, on this iteration, to keep the same development platform, and as I already had proven sending and decoding engines plus the Bluetooth keyboard hosting code, this would mainly be an effort focused on the graphics side of things. To start, I thought I'd try a Hello World display demo using the LVGL library. Now, with VS Code, the generalized approach to setting up a new project is to declare what they call dependent libraries, in this case LVGL. And that's the route I took. After some hours, if not days, of reviewing Waveshare's Wikipedia website, I had a demo program that compiled okay, but would not boot at all. Just a black screen and this message: I do see conflict. Driver NG not allowed to be used with his old driver. Now today it does, but in June 2024 the website didn't list either the display or the touch tip being used. So when that seemed to be going nowhere, I decided to back up, drop the dependent library approach, and instead download directly to my project's lib folder the website's version of LVGL, mainly hoping that their LV_config_h file, and maybe more importantly their ESP panel board custom.h files, contain the correct parameters to configure the dev board. That being true, then the LCD driver is the ST7262 and the touch tip in play is the GT911. This thinking was further reinforced by the website schematic having good agreement between the SP32's S3 pin and the display's ribbon cable connector designations. But, long story short, after making the switch, no joy. I was still seeing the I2C driver error. At that point, I started digging into how to fix it. Using examples from Expressive's website for their current I2C setup, I rewrote parts of the ESP display panel library code to work with Expressive's master I2C configuration connection scheme. This exercise brought life back to the display and would now go past the boot process and actually show something recognizable on the display, thus confirming I was back in the ball game. At this point, I was feeling pretty good about basic hardware initialization and setup, and went on to compile and run the original demo the display shipped with, but in truth knew next to nothing about the inner workings of LVGL. So it was time to dig in and work out how to build some basic display features that would be needed in the CW project. Arguably, the CW machine's most dominant feature is the text box, text area, or TA in LVGL speak. So that became the objective for the next series of coding efforts, which culminated with this little program. A text area that is periodically appended to with asynchronous changing temperature values. With this working fairly well, it was time to actually move to the intended project, the CW machine. Now, to be clear, I did this in a phased approach. First the decoder side, followed by the Bluetooth keyboard send side. Decoding and sending are really two independent programs, each having their own unique time-critical processes. This application is one where RTOS gets to shine, and programming gets interesting. Now, a bit of a disclaimer here. For the video, I'm simplifying the journey, so understand a lot is skipped over and the order of the issues covered here are not necessarily in the same sequence I addressed them. So, I don't know in the earlier text demo if it was obvious, but as the length of the text grows, the updates get slower. For the decoder, and also true for the send side too, this quirk needed to be addressed. There are, or were, a number of contributors to this, but for the video, the one I'm going to cover is capping the text area's character buffer. First step is use the LVGL command lvTextAreaGetText to create a pointer where LVGL is storing ASCII characters sent to the text area. Then, for later use, I make a second pointer to that same location, but notice this pointer is being cast as a void type where the first pointer was typed as a constant character. I need two pointers to the same starting point because the first can change as we progress through the code. Then I use the lvTextAreaGetMaxLength to recover what I originally declared as the maximum character length to be. Then using the string length function, we can now know the buffer's current character count. Then this little piece of math creates the variable delete, which, if positive, means the current character count has exceeded the set limit. Now, for this application, I would like to remove a whole line at a time, but because LVGL uses proportional spacing, it can be tough to know exactly how many characters make a line of text. What I found is 98 is a good average, so using a while loop I can look back through the first 98 characters in the buffer. And if there happens to be a new line character, I'll stop with it. But if not, the code using the memcopy function we'll shift the buffer's contents the appropriate number of characters to the left. Then we'll clean up things by making sure the characters buffer is null terminated and RTOS knows the buffer endpoints. I'll cover more about LVGL later, but the next issue I want to describe is really an extension of the original I2C problem. After having the CW machine up and running, I discovered it would crash after a couple of hours of operation. The error reported at crash was a write to address failure. What I found was in Expressive's I2C master.c file, it was allocating memory to create space to pass data to the I2C touch device, but on completion wasn't releasing this space. I corrected it by adding free commands within the methods that were doing this. This was the first of several mods made to what I call core code. The good news is, in this environment, the way the compiler works, if there are two copies of the same file, one in an Expressive package and one in your project's lib directory, the lib directory copy is the one that gets compiled. So this fix works, at least for the moment, for anyone else who downloads the project. For this file, it was fairly easy to move, but moving other core files can get complicated. What can happen is pulling a file out of its original location to run from another can make its supporting files invisible, and the compiler will fail. I ran into similar core code issues when I started working on the keyboard portion of the project. Earlier I said I had a working Bluetooth CW send engine using the ESP32, which is true. However, that version uses Bluetooth Classic. The S3 version of the ESP32 doesn't support Classic Bluetooth. With the S3, you have to use BLE or Bluetooth Low Energy. With the old ESP32 version, I could connect to a BLE keyboard and send, but that was about it. Since this version would be BLE only, I wanted a more robust connection. Also, since it's standard with HID devices to include the battery service, I wanted to capture and display the keyboard's battery state too. Now, to be clear, I'm not a Bluetooth expert, so I'm speaking solely from the experience of working with one BLE keyboard, Logitech's K380s. How representative of what's out there, I can't say. But getting Expressive's core code to do both the HID and battery profile proved to be challenging. And like the I2C code, I ended up making some tweaks to Expressive's Bluetooth code as well. Getting it to connect the first time in a session was doable. The problem comes when the connection is lost, and without rebooting the ESP32, you go to reconnect. Initially, I thought I wasn't closing the link correctly, and maybe that's the case, but what I found was in the BLE_HIDH.c file, it has the function ESP_BLE_HIDH device open. That, when the battery service is enabled, it won't pause correctly on a reconnect and wait for some of the needed GATT client events to occur before moving on to do some follow-on steps. As a result, things get out of sync and it ends up trying to open the device before it's ready. There's also another issue related to BLE reconnects, and that is a way to recognize a previously paired device during a scan session. To explain further, using an unpaired keyboard like the K380S, when it's advertising, it shows itself as an HID device, so the code knows it's a device to be added to the results list. However, once it is paired, in this case with the CW machine, the keyboard no longer advertises its type class. The only meaningful info returned is its device address. The good news is when the project pairs with the keyboard, the core code automatically stores the device address to NVS. The problem is for BLE devices at the application level, there's no ready way to test or compare the addresses being heard with those stored. However, Expressive's core code does have a function, BTC storage get BLE bonding key, that lives in the core file btc ble storage.c file. The bad news is it's not directly accessible to the project, so this is yet another file I copied to the project's local lib directory. Like all things computer, there's probably an infinite number of other ways to deal with this, but this is what I found first. To anyone who knows another way, your method would be a welcome comment below. Now back to LVGL and some other points that might be of interest. When talking about the LVGL graphics package, it's really hard to know where to start. As a newbie, I was clueless about how it goes about doing its thing. Like Expressive core code, there's tons of documentation, but to one just getting started, it's written at what I call the atomic level. Great for the expert that needs a quick check on formatting a seldom used command, but at that level it can be hard to see the forest for the leaves. That said, contained within the LVGL library there's a documents directory that contains a lot of reference material. Once you kind of get your bearings, it can be a great built-in resource, so even as a newbie it's worth taking a quick look just to get an idea of what's there. I think of LVGL as a large object or API sitting off by itself, which presents to you, the user, a set of objects that you can treat as a set of sub-objects or widgets in LVLG speak, each one with its own set of configurable attributes or features and event callbacks. LVGL keeps track of which widgets screen touches map to and provides simple interface commands to map your program-generated changes back to the display. In this project, go to the project source folder and check out the LVL message box init display method found in the LVL messagebox.cpp file. It concisely configures and calls functions needed to set up the Waveshare display. In my opinion, it cuts away a lot of the mystery that the website's use of generic files left me with. If you do choose to check out the init display function, two other areas in that same .cpp file worth noting are the include files shown at the top, especially the lv_config.h file, and the other is the build_lvgl_GUI method. It shows the call sequence needed to construct the project's main screen. Now, because I was basically porting an existing project to a new hardware environment, the original project already had a lot of code written around its own screen refresh task. I disabled LVGL's default refresh task and called its LV display refresh timer via my project's display message 2 function as needed in the CW machine project. If you're building a project from scratch, you might want to stick with LVGL's demo approach. Now, let's move on to a more generalized topic, code troubleshooting. Under the Expressive IDF, there are two tools that I haven't seen much said about, but I find quite useful. The simpler of the two uses the backtrace data that often gets posted to your USB serial terminal when the ESP32 crashes. Look for the text backtrace. Copy it and the number set that follows it. Then what I do is keep a text file which contains this command, extensa-esp32-elf-address to line, prefixed with the path to where the command is found on your computer. I use its absolute path, but if you have a path variable on file that lets the computer know where the command is found, then the path prefix won't be needed. Also note, I'm on a Linux machine. If yours is Windows, then the command needs a .exe suffix. The command is followed by 3 arguments. A -e, meaning you want to declare the input file name, which in this case is firmware.elf. So, following the -e, we have firmware.elf prefixed with its relative path. Note, from project to project, if the ESP device you're working with changes, then the path to firmware.elf will change, which is why we see the ESP32-S3-DevKit-1 in the firmware's path prefix. And finally, the last part is the backtrace data that the USB's serial port spit out. Running this command under Platform IO's new terminal menu option should return a listing of the code from the active task that was attempting to execute at the time of the crash. Sometimes this is all that's needed to come up with a fix. The second debugging tool is a bit trickier to use, but generally returns more useful reports. If you've never used it before, it may require installing some support packages, but in the end it works much like the first method, i.e. the program crashes, but instead of copying a set of magic numbers, you look for these lines in the crash report. The main thing you're looking for is ESP core dump saved to flash. Now, I need to digress a bit. You probably won't see this talk if you haven't first configured your project to save the core dump. You do that via running the menu config found in the Platform IO options window. So open the menu config tool and navigate to or open the component config section, and then down to the core dump and confirm data destination is set to flash. While I have the menu config tool open, this is a good time to also mention Waveshare wants you to configure a host of menu config settings to optimize the display's performance. Navigating the menu config maze can be a challenge. I've found 2 ways to help me find a setting or feature I'm interested in. The first method is to Google the config name and go to Expressive's reference site and then search again for the config setting. When found, the document will show the menu config path to the setting. The second approach is in VS Code. Open the SDK config file and do a search, Ctrl+F, on the config term. When found, it will show you its current setting and under what heading the term gets set in the menu config tool. For me, this latter approach is often the quicker way to get there. Now, back to how to use the crash report tool. So, when you see this verbiage in the crash restart talk, you can use the new terminal menu option in VS Code Platform IO and run this setup command. Notice that the first part of this is just the path to where the shell command actually is. This is the real command, the export sh. It'll generate a response that looks similar to this. If this is your first time ever to do this, it'll likely respond with an error message indicating that something was missing, followed by a suggestion of how to fix the issue. In Linux, I find the suggested fixes need to be modified where it reads Python to read Python 3.8, the version of Python installed on my computer. And don't be surprised if the first suggested fix leads to a second or even a third fix. But these errors, once fixed, are a one-time thing and won't happen in follow-on sessions. Now, going back to the original command, notice that if it ended in the environment IDF-PY permissions denied, if you got that, that's okay and you're ready to move on to run the actual debug command. In my case, this is how it looks. The real command is this espcoredump.py with the arguments port set to device TTY-ACMO and the baud rate, and then finally where the firmware ELF is located. Actually, I should say you're almost ready to run it. Before you do, connect your ESP32, in this case the ESP32S, to the computer, just as you did to flash it. And then, this is important, make sure no other serial monitor tool is actively linked to your ESP32. When the command executes successfully, the last line will read Done. Scrolling back to the top will look similar to this. As you can see, there's a ton of stuff in this report, and to be honest, I don't know how to make sense of most of it. But what I do find useful is, 1, it shows me how many tasks are active and their names. 2, where they are in their respective process. Most, if not all, but one, will be in some form of wait state. And 3, the first one, or the last one, depending on which way you're moving through the list, will be the active task that caused the program to abort. I'll come back to that, but first want to point out that the report also includes a listing of how deep each task had dug into its reserve or stacked memory, with the active task at the top of the listing. Some issues can be fixed simply by allocating more task memory. But if that's the case, usually the original crash report will indicate that kind of failure. So, back to the active task and what's shown in this report. As we can see, it's a drill down of which functions were in play at crash time, and their exit point to their support function, and where possible the values passed to the support function. This last piece can be a huge help in understanding what caused the failure, or at least point to what you might be monitoring next to further understand what's going on. As often, these crashes are happening far below the level of what you're consciously programming at. I'll stop here because the goal here was just to make the tools known. Now the last thing, for those who may actually be interested in the CW machine, and more specifically the decoder, in my opinion, is really the neat part of this project. This version and its immediate predecessor have what I call a post parser. To explain further, as the dits and das come in, the program tries to decode them using fairly standard Morse timing tools, and often that's good enough. But when this program senses a word break, it passes the dit-da collection over to the post parser, which has the advantage of now being able to look at the symbol set as a collection. Like the proverbial Monday morning quarterback, knowing what happened next often brings opportunities for better decision making than those made in the moment. So, as you watch the decoder do its thing, occasionally you'll notice a whole set of characters get picked up, so to speak, and replaced by something that hopefully is more accurate, or at least easier to read than what was originally there. For sure, sometimes it gets it wrong, but I like to think more often than not, it's better Well, that's enough for now. I hope you enjoyed the video, and better still, hope it encouraged you to do something with this display, or maybe even move further along in a project already started. Thanks, and good luck with your next project. One final comment related to I2C initialization discussed earlier. When I initially tried to compile a demo using LVGL and the ESP32 display panel library found at the Waveshare wiki site, the touch setup started with a call to panel begin in the app main function, which takes us to ESP panel begin, found in the ESP_panel.cpp file. It can be hard to follow, but it eventually calls the ESP panel bus _I2C begin function found in the I2C.cpp file, which is also part of the ESP32 display panel library. This second begin method is where things went sideways, as it calls a macro ESP_new_panel_IO_I2C, which is found in the ESP_LCD_panel_IO.h file and ESPIDF core file. Central to this macro is _generic. The idea behind this macro is, based on the variable type passed to it, it selects whether the I2C connection is set up using the legacy driver or the now current I2C master driver. As configured, the ESP32 display panel library wants to use the old legacy driver. For me, using the ESP32-S3-DevKit-C-1 compiler, it didn't recognize _generic as a keyword. At the time, I didn't either and opted to use the current driver. But because Expressive still supports the legacy driver, and if you hit the same speed bump, a simple workaround is comment out the call to the macro and replace it with a direct call to the setup function the macro would have used had it worked, which is what you see here.